Right, last week we studied standing waves. We studied principle of superposition. It tells us how to add up when the wave cross. We add the displacement to get the resultant displacement. We don't see the individual waves anymore when they cross. We see the resultant waveform. Then we look at standing wave in string, pipes, both closed and open pipe. Then we compare the fundamental frequency. Today we are going to determine the speed of sound using standing wave, comparing progressive and standing wave. There is a summary for string, fundamental frequency. Usually paper 2 is not that demanding lah. Paper 1 is more challenging lah. So you can memorize the fundamental will be faster lor. If not, you have to derive it yourself lor. Okay.
Sure.
For the string, the fundamental is V is the speed lor. Speed of sound over 2L lor. L is the length of the tube. Same as the open pipe. Open pipe and string are the same. Closed pipe is 4L. Then the general equation for string and open pipe is the same. Usually we use frequency lah, but objective one sometimes Cambridge a bit naughty lah. They want to use wavelength lah. Okay, so for frequency you multiply n by fundamental frequency lor. Whereas wavelength is fundamental wavelength divided by n. Same as open string and open pipe. Closed pipe is different. You have n is odd numbers only, whereas here n are whole numbers. Okay, so that one summarized for you. Standing wave in a closed pipe or closed tube is open tube or open pipe. Fundamental wavelength is 4L. Fundamental wavelength is 2L. Okay, so that's how we get our fundamental frequency. And what's the relationship between these two? Came out 1 year lah in objective. So you just multiply by 2 here, multiply by 2 here, then you get the answer lor. So for open pipe, fundamental frequency is double the frequency of closed pipe. Okay, so what this shows us is that different tube or the tube with different level of water can give you different note. Right? Higher note there, lower note there. Or in terms of physics, different pitch or different frequency. Okay. Experiment to determine the speed of sound. Right? This is a tube there. That's the first one, L1. First, you take it up so that it's filled up. Use a tuning fork. We look at the note easier. Note the frequency of tuning fork. Sound the tuning fork and place at the brim of the tube. You just hit it on the table. So you lower. This is the air column. This is a closed tube. This is the reservoir. End correction you don't need to know, but it doesn't matter. It doesn't mean that it doesn't. It's helpful lah if you know that, but you don't need to know if you don't want to know. Okay, so you first take it up so that it's filled up. Then you hit the tuning fork on the table, sound it, and then start to lower this air column. Increase the air column until you hear a loud sound. Adjust the reservoir downwards until a loud sound is heard. Then note your L1. Note the height of column L1. And repeat the above procedure and adjust the reservoir further downwards. So now the same thing, you get your L1. Now you want your L2. Right? So you lower it further. First you hit the tuning fork on the table or somewhere, something hard surface, and lower it, you hear a loud sound again. That's your L2. This what we have studied is the closed pipe constant length. This is the length that is different. Note the new length L2 of the air column. Determine the wavelength. The speed of sound is V equals to F lambda. Okay, that came out in 2006 June paper. We will do this experiment later on. L1 is plus. Actually, the antinode is slightly above lah. Right? Not exactly at the top there, but slightly above. That's why we add E there lah. E is called the end correction. So this is a quarter L1 plus E. Then this one is 3/4. Right? Same wavelength. Remember, these two are same wavelength. 3/4 wavelength. This is L2 plus E. So you subtract, right? You cannot use this equation without the E. Right? That's the reason why you have to subtract equation 2 by equation 1 to get that equation there. That's what you want. That equation is what you want, and that equation is given you as 32.4 cm. So that's how we find our wavelength. And then frequency we have already, you know the tuning fork, and can calculate the speed. So end correction, there's the antinode is a distant E above the top of the burette. Okay, differences between progressive wave and standing wave. Standing wave, displacement at nodes. At the nodes, the displacement is permanently zero. That's the node there. Permanently zero, it doesn't vibrate at all. Same here. Node permanently zero. Amplitude, each point along the wave has different amplitude of vibration from neighboring point. When you look between the nodes there, each point there or each particle there has different amplitude. The largest amplitude is at the antinode there. Same here. Okay. They are all different. Even if you look at here, between the node, all have different amplitude. The largest at the antinode there. Then phase. At points between successive nodes, the vibrations are in phase. There is a successive node. These two. All the points here are vibrating upwards there in phase. And all these points here are vibrating upwards in phase. Is vibrating downwards, is vibrating upwards. Whereas if you look at a point to the left and the point to the right, they are 180 degrees out of phase. Energy. The energy stays at the same position along the medium. Energy doesn't move. It stays there within the standing wave. Whereas progressive wave, right, it moves. Right? In terms of displacement, no point is at zero displacement permanently. You won't see a point at all. No point is at zero displacement. It may be zero. After that, it will be vibrating already. Amplitude. Every point vibrates with the same amplitude. Phase. The phase of neighboring points are all different. Right? They are all at different positions of vibration. We call phase. In terms of energy, the wave energy move along at the speed of the wave as the wave progress. Okay? The speed wave move along. So you can summarize the U in your note. Right? Memorize a few of them, about 2 or 3 of them. You memorize all of them, good, better still. Okay, before we do some question, let us listen to a video.
One lab that we'll be doing in the class is using a resonance tube to measure the speed of sound.
Can you hear?
It's a bit like how to say static, some static sound when you play.
Tapping sound. Let me change it to mono and see.
Sound. I can show you that setup really quickly. We'll start with a tuning.
How about that?
Yeah, I can.
Right now, okay, we'll start. That's your burette. This is a reservoir. You can also use this is a closed tube where you can adjust this length longer or shorter and then this is a loudspeaker.
Sure.
That's your power generator. They use different frequency This one is softer, partly because the tuning fork is very small. Right? With this one, you can adjust the amplitude using the power generator or oscillator, and then you can change the frequency. Okay.
A tube filled with water, and then turns out we can adjust the level of the water by raising or lowering this water reservoir. And what we find will happen is there'll be certain locations where volume changes a little bit. So let me show that. I'm going to hit this and put the tuning fork over top of the resonance tube here. So hopefully you noticed there was a specific moment where the sound became louder. And if you decrease the water level, you'll hear it again. There it was again. I'll try to make it happen louder again in case you missed it the first time. I'll raise the water level back up.
That's the water level.
Okay. So we've seen here, and you will measure in the lab, several locations where it does this. What's happening here is I'm trying to get a good standing wave going in this resonance tube. For a tube that has one end closed and one end open, ideally you would like the open end to be an antinode and the closed end to be a node. It's like these pictures here. If you have a tube of a certain length, you can fit 1/4 of a wavelength in exactly, or if the tube is a little bit longer, you can fit in 3/4 of a wave. That's the rule for tubes that are closed at one end and open at another end. You want to be able to fit an odd number of quarter wavelengths in there. So we'll be doing that. These tuning forks are 1,000 hertz. So through this bit of experimentation, we can figure out how big half a wave is, the distance between those two loud spots, and then we can use it to determine the speed of sound. However, for my video demonstration purposes here, I would rather do this in a little bit more scaled up fashion. So we have the cardboard resonance tube out here, which can demonstrate the same thing a little bit more dramatically. It's the exact same effect. I'm going to have a tube that's open on one end, so you can completely put your hand in it. and it's closed on the other end. And we can adjust the length by pulling this inner tube insert in and out. All right. So the way I'm going to show this off is with a speaker. Instead of using a tuning fork, I'm going to use a big old speaker here. And my function generator is set at 440 Hertz. This is a Concert A, and you'll notice I can just turn it on, and I can also make it louder by messing with the amplitude knob of this function generator. Louder, and quiet it down. But that's not what I'm not gonna mess with this any further once we start the demo. I'm gonna do the exact same thing did with the water tube over here. I'm gonna adjust the length of the tube, and there will be certain spots where, if the tube is just the right length, you get constructive and destructive interference just the way you're supposed to, and a standing wave of maximum amplitude is set up. And we'll be able to hear that. So I don't really care how long this tube is. All I care is how far do you have to lengthen it to go between one loud position and the next, because the difference between those will give me half a wavelength. I'm messing with a frequency here of 440 Hertz. We will find out what the wavelength is, and hopefully, even though this is a really quick and crude measurement, we can get a speed of sound similar to what we expect. So what I'll do is I'll put the, make sure the amplitude's okay. I'll put the speaker on one end and then mess with the other end. You can hear as I move this in and out, there'll be some loud places and some quiet places. So let me do that. So I'm not touching the amplitude knob anymore, just adjusting the length of the tube. Now it's not as loud. Okay, so I stretched out this tube from, 41 centimeters exposed to 80 centimeters exposed. So okay, there's 39 centimeters of difference in the two positions. That means that 1/2 of one wavelength is half a wavelength. So the wavelength is double this, so 39 doubled is 78. So 78 centimeters is 0.78 meters. Okay. So just to see if we get something reasonable here, I can make an estimate of the speed of sound. If you take 440 Hertz times 0.78 meters, if you go through your calculator and you put those numbers in, it's 343.2 meters per second. And depending on room temperature, we usually take the speed of sound to be either 343 meters a second or 344. So we came actually within 1 meter per second of all of the accepted values for the speed of sound here. And all it took was just a quick measurement with a cardboard tube. I mean, the fancy part is knowing that I was playing exactly 440 Hertz from here. But by checking the difference in the tube lengths where you have a good standing wave set up, we can figure out the wavelength We know the frequency, and you can get the speed of sound. You'll be doing the exact same thing in the lab with the water tube. Measure the separation between the loud spots, get the wavelength from that.
If you find yourself struggling to remember names or important tasks, or if maintaining concentration feels increasingly challenging, it's time to pay close attention.
Okay, let's go back to our okay. This is just can you see the diagram?
Yes.
Okay, then we are okay already. This think of your mode of vibration as your displacement distance graph. Then how does the pressure varies? Just know roughly lah, don't need to be too particular. There's nothing mentioned in the syllabus. So that is your displacement distance graph. That's a pressure graph. Okay, this is for closed pipe variation of pressure. So where the antinode is, there is high pressure. So where the node is, there's zero pressure. Right? So anyway, we won't go too far into that. But vibration of air particles in the standing wave, if we look at the first harmonic for open pipe, open tube, open pipe, sound waves are longitudinal waves. Remember that? The first harmonic shows the displacement distance graph. This is a displacement distance graph. Right? So depend on which one you are reading. We are using the blue one or you are using the red curve. Displacement of sound is horizontal. Taking upwards as positive, yeah, normal convention, upward as positive, and to the right as positive. Right? Upwards as positive, and then to the right as positive. Arrow show the displacement of particle of the arrow show the displacement of the particles of the air, either all points to the node or all away from it. Right? If you look at the blue one, at this point there, there's the amplitude. So there's the amplitude. At this point there, smaller amplitude, there's the amplitude. There's the node there. It's not moving. Right? This one is negative. The negative is going to the left. Same here. Negative is going to the left. Or if you look at the red one, so it's either all the arrow pointing towards the node or pointing towards away from the node. Okay, so normally we will do it, we will show the vibration rather than just show, how it looks like. But exam is usually this form. Okay, this is remember at the node there, the largest vibration. Same at the end there, the node largest vibration. In between there will be smaller vibration. At the node there will be zero. Right? At the open there is antinode, largest vibration. Or for the second mode, same thing. Okay. Okay, let's just summarize it up. Right? That's your wavelength, cross to cross. This is half a wavelength. This half a wavelength also, or from maximum to a minimum is half a wavelength. This is a quarter of a wavelength from maximum to 0. Did you manage to do the worksheet?
No, I just came back.
And we will do it together. Okay, number 9. What is the wavelength of the standing wave formed in the open pipe?
Huh?
On the page.
104, right? Sorry.
204. Page
204, okay.
What's the answer? What's the length of the tube?
30 cm. Oh, okay. What is wavelength?
What is the wavelength of the standing wave formed in the open tube?
60.
Right? If we look at this graph there, or this curve, from here to here is one wavelength, another half a wavelength. So it's one
Oh
and
yeah,
a
one. Oh, okay.
30.
Yeah.
So it's 20 cm now, B. Okay, we are going to be cut off in 10 minutes time.
Yeah.
What's the wavelength of standing wave formed in the closed tube?
Yeah.
What's the answer? From here to here is one wavelength. Right? Yeah, then look at this.
1.5. And then so.
No, 1.25. This is a quarter.
Sorry.
One and a
Oh
quarter.
yeah.
What's the answer?
But this one is a closed pipe.
This is a closed pipe. This one wavelength plus a quarter.
Closed pipe must times 2, right?
So 5/4
Uh,
lambda 30.
oh.
Then it's just multiply by 4/5. Lor. Get rid of that or cross multiply. 4/5 is 20. Answer is A. Lor. Okay or not?
Okay.
A long tube. This is partial paper 206 June. A long tube is fitted with a tap. The tap is filled with water. The tuning fork is sound above the top of the tube as the water is allowed to run out of the tube as in figure 6.1. Right? That length is 32.4. A loud sound is first heard when the water level is as shown in figure 6.1. Right? That's figure 6.1. And then again when the water level is shown in figure 6.2. 6.1 illustrates the standing wave produced in a tube. Sketch the waveform. Sketch the form of the standing wave set out in the tube. On figure 6.2, mark the letter node position of any nodes of the standing wave. That's what you're supposed to do. Lor. The node there, right? Draw the diagram. Lor. So you
So the
don't
node is like
say again.
the node is at the surface.
The node is this is a closed end. Water surface is a closed end. So that's a node. Same here,
Okay.
there's a node here. Right? Don't need to know all this calculation. You just need to know this is the same. This is the same. So this is half lambda. Half lambda. L2 minus L1. Half lambda. Okay. Label that. Antinode no need lah, since they didn't ask you to do antinode. You just do the N will do lor. Frequency of the tuning fork is 512 Hertz, and the difference in height of water level for two positions where loud sound is heard is 32.4 cm. Calculate the speed of sound in the tube. Right? Half lambda is that 32.0. Change it to meter, 0.3324 meter. So times 2, you get 0.648 meter. Length of the air column in the tube in figure 6.1 is 15.7 cm. Suggest where the antinode of the standing wave produced in the tube in figure 6.1 is likely to be found. So you have to calculate your right? You have to calculate your speed first. Sorry, we have calculate wavelength, forgotten the speed. Calculate the speed, F lambda, right? That's the frequency. And then there's your 2 times that. So that is the speed.
300.
300 or 320. This is 3 significant figure. Your answer should be 332.
Okay.
Right? Lambda is 0.648 meter. So a quarter lambda. Right? There's a quarter lambda. Quarter lambda is 0.
0.162.
Get that? So it's 16.2 minus 15.2. So it's the antinode is 0.5 cm above the top of the burette. This is called the end correction. Okay. Any
So how do
comment?
you know it's quarter?
Say again.
How do you know it's quarter?
Okay, let's just go back to that. This is a quarter. That's maximum.
But how do you know it's 1/4?
Quarter wavelength.
How?
Forgotten
Oh
already.
yeah. The wavelength, right? Oh yeah. Oh my
Quarter
god.
wavelength
I
is
thought
L1.
even
Quarter wavelength is L1. That's what we are doing.
got a one full oscillation. Okay.
So 1/4 wavelength. So 1/4 you divide this by a quarter, you get 16.2 cm. So 16.2 cm is minus 15.7. So 0.5 cm. Okay. Okay. Right? Same thing. You use equation. As I say, you don't need to know all this. Okay. State how the speed of sound can be determined. Note the frequency of tuning fork used. Sound the tuning fork. Sound means you hit on a table or hit on some hard surface. And place on the brim of the burette. Lower the water level until the loud sound is heard. Note L1. Right? Repeat steps 2 and 3. 2 and 3. Sorry, 2 and 3. By further lowering the water level to L2. Okay, then just L2 minus L1. If you get half lambda is L2 minus L1, then speed is F times F. Okay with that?
Oh, okay.
You need to know about all these equation. Just half lambda is L2 minus L1. Good enough already. That's the reason why they tell you do step by step. Okay, what's the correct answer for this one?
I think it's
Point Q vibrates with the largest
it's
amplitude.
it's either A or B.
Cannot be. Q is not the largest amplitude. Largest amplitude is at the node
Oh,
here.
oh yeah.
Points P and R vibrate in phase.
Teacher,
Yeah.
but Q is the largest amplitude among all of them.
No, largest is at the center here, maximum here.
No, Q is the largest among PRS.
In terms of amplitude, now R is the largest. If we do consider
Oh
negative,
yeah. Oh, negative was okay. So I think it's B.
P and Q are in phase. S is antinode, no. S is the node. Horizontal distance between R and S. R and S is half a, no, not half a wavelength. It's a quarter of a
It's a
wavelength.
quarter.
Okay, will be cut off any time. So during your